Okay, I'm back again. I was being a little dumb. I want to conclude from this that the graph I have left is not just the empty graph with no vertices. And of course, once I establish that the number of edges is bigger than 0, then it simply can't possibly be the case that n prime is 0. Because if n prime is 0, then the number of edges left would be 0. I was just being, you wouldn't believe how long it took me to think about that. If the number of edges is bigger than 0, then n prime is bigger than 0. So what I've done is I've taken a graph where the average degree is bigger than k minus 1, but there might be some low degree vertices. And simply by deleting one after the other all of the low degree vertices, what I have obtained is a new graph g prime, which still has average degree strictly bigger than k minus 1. Why? Because now the number of edges of g prime is at least n prime k minus 1 over 2. So I still have the property that the average degree is very high, but now I have even more. I have the property that the minimum degree is fairly high because I have deleted all the vertices which have low degree. So now there's some chance that I can find a long path in the graph by some kind of process of, well, let me try to start building a path, and as the path goes on, when I get to the last vertex of the path, I know that that last vertex has high degree, so there's a good chance that I'll be able to continue along to a new vertex, a vertex that I haven't visited previously. I wouldn't have been able to do that if all I knew that the average degree was high. Okay, so this is a very useful trick when working with graphs where it might be annoying to have to deal with the vertex of low degree. You can often eliminate the vertices of low degree and still be working with a quite substantial graph. So this graph G prime, not only does it have high average degree and high minimum degree, but we can actually also assume that it's connected. So I'm going to assume, without loss of generality, that G is connected. And why is that a valid assumption? Well, what I am saying in this condition, that the number of edges is number of vertices times k minus 1 over 2, I'm saying that the ratio number of edges to number of vertices is at least k minus 1 over 2. Now, if the graph is disconnected, then at least one of the components is going to have ratio of edges to vertices inside that component be bigger than k minus 1 over 2. Because if every component had the ratio being smaller or equal to k minus 1 over 2, then the global ratio would also be smaller than or equal to k minus 1 over 2. If everybody on the Yankees is batting under 300, then the Yankees batting average as a team can't be more than 300. So I'm going to assume without loss of generality that that G prime is connected. Okay, and now what I want to do is show that G prime has a long path, the path on k edges. So let P, which has vertices, let's say V0, V1 up to Vt, be a longest path in G prime. So case 1 is that T is bigger than or equal to k, and if T is bigger than or equal to k, then I'm golden, because that's automatically a path of length at least k. A path with at least k edges. So case 2 is going to be when T is less than or equal to k minus 1. So that's the case I'm going to have to try and do some work on. And what I'm going to try and do is argue some kind of a contradiction. Okay, so here's my picture. I have my vertices v0 up to vt. Here's v1, here's v2, and so on. Vt minus 1. And this is the longest path. So I know the following. All neighbors of v0 are contained in v1 up to vt. And I also know that all neighbors of vt are contained inside in v0 up to vt minus 1. Why is that? Because if v0 had a neighbor that wasn't in here, then I could just build a longer path. If vt had a neighbor that wasn't in here, I could build a longer path. Okay. Could I have v0 vt be an edge of g prime? Well, I'm going to argue that that simply can't happen. So what would happen if v0 up to vt was an edge of this graph? Well, then I would have v0 through vt actually be not just a path, but be a cycle. Now, notice that because v0 to vt was a path, I argued that all of the neighbors of v0 have to be inside the path, and all of the neighbors of vt have to be inside the path. But now if I have a cycle, I can break the cycle. I can start v2 up to vt, back to v0, along to v1. And that will give me an equally long path to the path I had before. And the same argument will show that v1 has to have all of its neighbors inside in the path, and v2 has to have all of its neighbors inside in the path. But then I could also break the path by starting it, break the cycle rather, by starting it v3 goes to vt, goes to v0, goes to v1, goes to v2. And then this would be a longest path. And so I would argue that v3 has to have all of its neighbors inside in the path. So the fact that I have a cycle means that I can produce an equally long path as v0 through vt, starting with any of the vertices in the cycle. And that means the same argument will always show that each vertex of the cycle has all of its edges inside the cycle. So the conclusion is that if v0 vt is an edge, then all neighbors of vi are in the path for all I. That means that none of these vertices see anything else in the outside world. And since I'm assuming that I'm working with a connected graph, that means that this is the entire world. So that says that the vertex set of G is exactly the set v0 up to vt. And let me count the number of edges. The number of edges in G prime is the absolute worst it could possibly be is if I have every edge present, and that would give me t plus 1 choose 2, which is, let's see, I want to get a contradiction to the fact that I have more than n prime k minus 1 over 2 edges. And let's see, so this is equal to t minus 1 over 2, and oh no, it's not. Sorry. That's good. This wasn't working out. T plus 1 choose 2 is t plus 1 times t over 2, and I know that t is less than or equal to k minus 1, so that means that the t over 2 gives me the k minus 1 over 2, and the t plus 1 gives me t plus 1 is exactly the number of edges. So that tells me that the number of edges in G is at most n prime k minus 1 over 2, which is a contradiction. So I actually know that v0, vt is not an edge of this graph. So what I have is a longest path from v0 to vt. Because it's the longest path, all neighbors of v0 are inside the path. All neighbors of vt are inside the path. And I've just argued that it can't be the case that v0 is joined to vt. So actually, all of the neighbors of v0 come from v1 up to vt minus 1. And all of the neighbors of vt come from v0 up to vt minus 2. And time has run out. So what I will pick up on, I'll pick up on this at the very beginning of next time on Monday. And I will use a pigeonhole argument to show that I'm going to be able to find a neighbor of vt which is one below a neighbor of v0. And that's going to be by pigeonhole principle. And that's going to give me a cycle. And we've already seen that it's impossible for all of these vertices to form a cycle. So that's going to be the argument that finishes the proof by contradiction in this case too. But I'm well out of time, so we'll pick this up on Monday.